Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical properties. To assess these properties, various principles of measurement are used. One of these principles is pH measurement according to the potentiometric principle. The principle can be traced back to 1909, when the Danish chemist Søren Sørensen introduced the so-called hydrogen ion exponent pH+, to describe the concentration of hydrogen ions in a solution. This was the basis for the development of the conventional pH scale. In 1889, Walter Nernst formulated the Nernst equation that for the first time related electrical voltage to ion concentration. The Nernst equation derived for pH is the physical basis for pH measurement according to the potentiometric principle. Potentiometric pH measurement is the measurement of a potential difference using so-called glass electrodes or non-glass electrodes. In the case of glass electrodes, the pH-sensitive element is a glass bulb that is fused to the end of a glass tube. The electrode is filled with a neutral potassium chloride solution buffered at pH 7 and contains a silver chloride wire that forms the electrical connection. The reference system is located in the outer glass tube and also consists of a silver chloride wire in a potassium chloride solution. A so-called junction protects the reference system from the medium to be measured without disconnecting the electrical connection between them. The pH value is calculated from the potential difference between the reference system and the measuring system. Let's take a closer look at the pH-sensitive glass bulb to understand how this potential difference is formed. Diluted hydrochloric acid, for example, contains large negatively charged chloride ions and small positively charged hydrogen ions. When the pH sensor is immersed into this acid, the hydrogen ions are able to penetrate the boundary area of the glass membrane, the so-called gel layer. The considerably larger chloride ions remain in the solution. The result is a charge separation. The same process occurs on the inside of the sensor with the neutral solution buffered at pH 7 that has a constant concentration of hydrogen ions. If the hydrogen ion concentration, hence the pH value on the inside, differs from the concentration on the outside, a measurable potential difference forms. If the hydrogen ion concentration on the inside is lower than on the outside, as shown here, the measured solution is acidic with a pH value lower than 7. If the hydrogen ion concentration is identical on both sides, no potential difference forms and the measured solution is neutral with the pH value 7. The measured solution is basic if the hydrogen ion concentration inside the glass bulb is higher than in the measured solution. pH measurement with non-glass sensors is based on so-called ion-selective field effect transistors, short ISFET. They use a MOS transistor arrangement, which contains a pH-sensitive layer instead of a metal gate. Positive hydrogen ions forming at this layer cause the charge to be separated on the other side. As a result, the area between source and drain becomes conductive. The resulting flow of current is in direct proportion to the pH value of the medium. Just like the glass sensors, the ISFET sensor also needs a stable reference potential. The potential that forms at the ISFET can then accurately be measured against it. The reference system is also protected from the measured solution by a so-called junction. The potentiometric measuring principle by Endress+Hauser enables highly accurate pH measurement for better product yields and less waste. We offer a solution for all applications, even in those industries that do not tolerate glass. For further information on liquid analysis, and the latest pH sensor generation featuring MemoSense technology, visit the Endress+Hauser YouTube channel or www.endress.com.